Hello, everyone. So I'm on a bit of a time crunch today, so I'm not going to delay too much. Let's just get straight into it. Okay, let's see. For day 18, I don't recall there being too many interesting tricks. I think there are a couple of ways to do this that don't involve shoelace formula, but they're all considerably more complicated. I think the main one is that for part 2, since the movement directions are so long, a trick that you can do for problems like this is a coordinate compression, where basically if you imagine we have a really large trench drawn something like this, then if you were to try to use like a fill algorithm to fill out this entire thing, it would take forever because the dimensions would be too large. But what you can do is, if you only consider the coordinates where something happens, so for the x coordinates, that would just be these 5, and for the y coordinates, that would just be these 5 as well, then you can essentially just remap that onto a 1 by 1 grid. And so you'd get something that looks like this. And now, regardless of how large these is, this could be like a million, for example. This could be like a billion. Regardless of how large the dimensions are, you end up just getting a 1 by 1 grid. And since the number of instructions isn't large enough for you to have too many coordinates on your compressed grid, what you can do is you can just fill that, which will be relatively fast. And then for each cell that is filled, you just decompress and figure out what it corresponds to in the original grid. And so that's one way of doing this problem that doesn't require shoelace formula, but it is rather complicated in comparison, at least I think. So I'm just going to revisit how you do this with shoelace instead. So because the fill algorithm is not very interesting, breadth first fill we've used that about half a dozen times probably this year. And or maybe not this year, but it's a very common thing in AOC. I think this year actually maybe it wasn't used as much as usual. But the main thing is this coordinate compression thing. I don't think there were any problems this year that required us to use that trick, but it is good to keep in mind. Essentially, the idea is just if your inputs are large numbers and you're working on some sort of coordinate system where things are spaced really widely apart, you can apply coordinate compression by just only looking at coordinates where something of interest happens, in this case where any turns are. And then you can just compress anything between two adjacent coordinates into just one space. And then when you apply whatever operations you want to the compressed grid, you can then just take each 1 by 1 and map it back. So this works if there are few points of interest and your grid is relatively small because you need to map every single element back. But it helps you with large inputs that are spaced really far apart. Of course, for this problem, since it's basically just asking for the area, we can do this a lot more easily. Let me set the stream topic. Okay. And so, yeah, we have basically for each line of input, we have 3 things separated by spaces. The last thing we'll ignore, so it's just going to be direction, number of steps, and some blank that we don't care about for the first part. And then something interesting that someone did note, let me take a look at chat. With 2,000 steps, you might get up to k squared. Squares. Yeah, coordinate compression for this problem is still going to be slower than shoelace, obviously, because shoelace is really fast. It's linear time. Yeah, you could still get a considerable slowdown, because the thing is, coordinate compression doesn't work nicely if none of your steps line up. Like in this example, none of our vertical lines line up. It works better if you have some amount of duplication. So in this example, it would be a bit better because these would line up. But in this case, none of them line up, and so you end up with a lot of squares that you need to map over. So yeah, something that someone did notice is that basically when you do shoelace, you have some polygon with a bunch of points, and then you need to apply an operation for each pair of adjacent points. But in our instructions here, I believe we always return back to the original point. That's part of the guarantee of the way we're digging our trenches. And so that allows us to simplify our calculations a bit, because what I did in my video was I took every pair of adjacent points and then I also wrapped around at the end. So I was looking at the origin point against itself. This doesn't affect the answer, but we can simplify it a bit by just ignoring the last point, or rather we can treat it, I think this will be a bit easier to explain once we actually get into the code. But basically the last point and the first point are the same. And so we don't need to consider the last point and the first point separately, like so. We can just apply it to every pair of adjacent points, not wrapping around the end. And then we just skip the last and first point against each other. Normally, this would be the last point and this would be the first point, so you would need to wrap around. But in our case, we close it off at the end, so we don't need to consider them separately. So yeah, we still want to keep track of all of our points. And the reason I'm not using complex numbers for this is because when we do shoelace formula, we need to take the x and y coordinates separately. And so at least in my opinion, it doesn't really make it any easier. One way I think we can make it a bit easier though is if we store the x and y coordinates separately, because we need those separately all the time. And so this might make our formula at least look a bit easier to understand. And that also lets us so you don't necessarily need to know too many algorithms, but inevitably you will need to know some number of common tactics like dynamic programming, BFS, stuff like that. If you don't know the shoelace formula, that's fine. Although if you look up like calculate area of polygon, you probably will get something along the lines of shoelace. Oh, no, this is for regular polygons. Calculate area of any. Yeah, seems like they're all about regular polygons, so maybe it's not that easy to look up. But in any case, oh, no, I think this might be it. Yeah, you can find these formulas by looking up something roughly along the lines of what you want. From Shapely import polygon. Yeah, there's also the possibility that you can just find Python libraries that just do exactly what you want. But either way, to solve this problem without using any formulas, you can definitely get part one by just using a fill algorithm. For part two, if you don't know and can't figure out how to get the area of a polygon on its own, you would have to figure out coordinate compression, which is probably harder than finding the formula to get the area. But I do know that a couple of people that I talked to did use coordinate compression for this part. But yeah, in general, you can't really get away with not knowing any algorithms. So inevitably, any sort of competitive programming environment is going to require you to learn algorithms. At least in my experience, the AOC is actually a bit better in this regard than like traditional coding contests. Usually the AOC allows you to know fewer algorithms and do stuff more with just your own problem solving skills. Okay. So now we can say if the direction is right, then actually this is probably an easier way of doing it. Okay, so for we can do if d is r, then we'll do x plus equals 1. And if d is left, we'll do x minus equals 1. So what I'm doing here is I'm just going to mutate x and y to the new current point, and then each time we'll just append it to x and y. So y minus equals 1, L if d is equal to. And then we just do x is dot append x and y is dot append y. Let me get the test data. And so those are the x and y coordinates that we have separately. Sorry, this is, forgot to get the integer value for n. This is correct. And so if we print out there we go. Those are our individual points. So we start at 0, 0. We go to the right to 6, 0. Then we go down by 5 to 6, negative 5. Then we go left by 2 to 4, negative 5, and so on and so forth. So this is correct. And we see that we end up at 0, 0 again. If we run this on our real input, we see that we also end up at 0, 0 again. And so the shoelace formula, it has a couple of different forms. I think there's actually an easier form than the one I usually use. Yeah, so actually let's spend a bit of time going over exactly how the shoelace formula works. The basic idea of it is if we have some polygon and we're trying to find the area, there are two approaches to it. I'm not going to go over the exact derivation in the interest of time, but just a brief explanation so that it's not just pure magic. So if we consider drawing two lines down to the x-axis, now we basically have a trapezoid that is put under this curve. And so we can take these 2 points and their points at the x-axis and calculate the area of this trapezoid. Now for the next pair of lines, this is going left. And so we can see that basically if we start at this point and go clockwise around the shape, if the edge goes to the right, then the area under it is part of the polygon. If the edge is going left, then the area under it is not part of the polygon. So it gets excluded basically. So now we take the area of this trapezoid and we subtract it from the area, which we get by the sign when we subtract the x values apart from each other basically. And then if we look at the next set of lines, this one's going right, so the area under it is part of the polygon, so we add this trapezoid. And then looking at the next two lines, sorry, the next line, this area is outside of the polygon, so we subtract it. And then finally for this one, it's still under, so we subtract it as well. And so what we end up with is basically we took the area of this entire thing, this entire trapezoid here, and then we subtracted this. So right now this is in excess by all this amount here. We subtract this part, which means that we're now missing this little triangle here. But then we add it back. And so after we add this part back, we are now in excess by this amount here, this amount here. And so then when we subtract these two parts, we get the area of the polygon. And so the idea behind shoelace formula is essentially we just deconstruct the shape into a bunch of trapezoids. Each trapezoid has the top edge being one of the edges of the polygon, and its side edges and bottom edge being the x-axis and the two lines that you get from drawing down from the endpoints. And then depending on which way the trapezoid is facing, some of them are added, some of them are subtracted. It doesn't really matter which, as long as we're consistent about the direction we're going in. And so that's the general idea behind the shoelace formula. There's also a way to do it with triangles. It gives you a similar derivation, but it's roughly the same idea, where we basically just deconstruct the shape into a bunch of smaller shapes that are easy to calculate the area for, and then we just need to figure out which ones are added and which ones are removed. So the formula that I was previously using, I believe is, this one here, which I think is not necessarily the easiest way. I think this one might be simpler. Yeah, this one, for each x we take the difference between the y after and before it. This one, for each pair of points, we take the sum of the y and the next y, and then the difference of the x and the next x. Okay. So now we can do for I in range length x's minus 1. So we exclude the last one because it's 0, 0. So then we basically just go through each pair of points, and then we just do y I plus the next one. And then we take the difference of the x's. And now if we take the sum of that, we should get double the area. So we got negative 84. And the area we're looking for is 62. Okay, so the way I solved this issue, so let me go over what the issue with this current approach is. So let's say we have a relatively simple trench consisting of, let's say, these cells here. So let's say we have this trench, and so the number of points here is 15, but currently if we take the area, we're basically putting the points and edges of the polygon in the center of our cells. And so the area inside here is going to be 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 8. So it's not going to be the correct value. And so the way I solved this during the video was using Pick's theorem, but there's actually a much easier way to do this. So if we look at the area that we're missing, basically for each point on the outside edge, we are missing half an area, except in some cases. So whenever we have a rightward turn, or any turn that, like a turn that's basically has the area on the right side of it, like inside of it, we are missing an extra quarter. And then whenever we have a turn in the opposite direction, like a concave turn, we have a duplicate count of a quarter of an area. And so the part we need to figure out is how many of these turns exist. And this actually turns out to be surprisingly easy. The number of times we turn clockwise minus the number of times we turn counterclockwise has to be 4. Because we need to close off the loop, and in order to do that, we inevitably have to make a complete turn. We can't make 2 complete turns because the polygon would have to intersect itself for that to work. And we know that there... I don't know if we're guaranteed that there are no intersections, actually. But I think we can assume that there are no intersections. If we want to ensure there are no intersections, this problem actually becomes a bit harder. If you want to deal with intersections like this, for example, I'm not sure if you can still use shoelace formula. Yeah, let's not think about this. I don't think I have time for that today, unfortunately, but there are definitely still ways to solve that. But for this specific problem, where I'm pretty sure we're guaranteed no intersections, the number of rightward turns is just 4 greater than the number of leftward turns. And so basically all of them cancel out. And so we have, in our example here, 1, 2, 3, 4, 5 outside corners and 1 inside corner. So this lines up with what we're expecting. And in all cases, because the number of turns we're making is in total 1, anytime we make a leftward turn, we need to cancel it out. And so all of the leftward turns get cancelled out by a rightward turn. And so we're just left with always exactly 4 outside turns that don't get cancelled out. And so the amount of area we add is just half of the number of boundary points plus an extra 1. Now, if you recall from how I did it with Pick's formula, we had the area using shoelace. And we know that according to Pick's theorem, the area is the number of interior points plus half the boundary points minus 1, which is this approach here using the turn amounts is actually just a special case of Pick's formula that works if all of your points are lattice, are integer points, and also all of your edges are like axis aligned. This is true in general, but we just have an easier time demonstrating it here. And then using this, we determine that the number of points, basically the area of the expanded trench, is going to be I plus B, because it's the number of interior points times plus the number of non-interior points. And so that was equal. We had I is equal to A minus B over 2 plus 1, and so this was equal to A minus B over 2 plus 1 plus B, which is equal to A plus B over 2 plus 1. So this approach here that we did with the number of turns is essentially just a faster way to get here from, instead of relying on Pick's theorem, we just use our understanding of how many turns need to exist. And so we can bypass using Pick's theorem and just arrive at this formula directly. And the number of boundary points is just the sum of all of these n. So we can just do b equals 0, and then each time it's just b plus equals n. And so now we just take the area, which is, we need to take the absolute value of this, because if we turn the wrong way, like remember how I showed Pick's theorem, shoelace formula using this thing where we mark this as part of the trapezoid? If we go in the other direction, then we mark this as part of the trapezoid, this is part of the polygon, and then we remove this. And so because we're doing it backwards, we'll end up with a negative area. And so it's important that we take the absolute value here, because it's completely random whether we get a positive or a negative area. And so then we divide that by 2. That's just part of the formula. And then the number of boundary points is known here, and so we end up with just A plus B over 2 plus 1. And so that's part 1. So to recap, basically shoelace formula, if you want a deeper explanation or a derivation of it, just look at the Wikipedia article. It's pretty thorough on shoelace formula. And other than that, the main observation here, which someone showed me in a YouTube comment, I believe, is that we always have 4 outside corners. Any inside corners get canceled out by exactly one other outside corner. And so all of these will pair up, and we'll be left with exactly 4 extra corners on the outside. And this is just because our polygon needs to close itself. And since we're assuming non-intersection here, which I believe is valid, we'll always need to make one complete revolution clockwise. Or counterclockwise, it doesn't matter. And so that just tells us that we need to add half the boundary points, and then add an extra 1 for all of these 4 corners added together. And again, if you don't want to rely on this intuition, you can just use Pick's theorem. And part 2 is basically the same. We just need to change our input handling. So, like, basically, the way this solution is set up, the only thing that needs to change is how we compute d and n. Basically, our solution can be split into 2 parts. We have a parsing part, which, given a line of input, determines what the direction and the number of steps are, and then everything else around it is completely independent of this part. So one general tip for AOC is, even if you can't predict what part 2 will be, in this case, it's pretty hard to predict, actually, because I was assuming that we would have to do something with the colors, is try not to make your components too heavily integrated. So in this case, by keeping the input handling and everything else separate, if we happen to need to use this whole area calculation thing again, it's very trivial to just replace this part. And so that's exactly what we'll do. For part 2, we literally just grab the second part, this part, we'll call it, I guess, color. And then, again, the color is given in this format. So we'll want to get rid of the brackets and the pound sign first. So like that. And then, how was this done again? The last hexadecimal digit encodes the direction. And so the direction is, if we take the last character of color, then convert it to an integer. 0 means R, 1 means D, 2 means L, and 3 means U. And then for N, we just take the remaining 5 digits in hexadecimal. And so it's just the first 5 digits of color, or you can say all but the last digits, the same thing. And then the Python int function has a built-in input for the input base. And so we can just take it in base 16. And that will give us our answer for part 2. Yeah. So once you know shoelace formula, this problem is pretty straightforward, because it's literally just you're given an input as a polygon and you just need to find the area. The only interesting observation for this problem is mostly this winding thing with the number of corners on the outside. Again, just to make it absolutely clear, we are making the assumption here that there is no intersection of the polygon. If the polygon intersects itself, I don't know if shoelace formula even works anymore, and this thing here definitely doesn't work. Although, actually, there maybe is a chance that it does, because if it does intersect itself, then these outside corners won't be counted, but they also shouldn't be counted because they're already in the polygon. You know, just for fun, let's see if it would work on a self-intersecting polygon. Okay, so this is what we're going to do. So we're going to go right 3, down 2, left 2, up 1, right 1, down 2, left 2, up 3. Let's run this as a test case and see if it works. So right 3, down 2, left 2, up 1, right 1, down 2, left 2, up 3. And this should give us an area of 15. Oh. Okay, so it doesn't seem like it works if we have intersection anymore. Okay. Yeah, that's about what I expected, unfortunately. Well, in any case, it seems that it's intended for there to not be any intersection. Yeah, unfortunately it's not guaranteed, but I don't think I have the time to think about how we can generalize this to not care about intersections. So let's just go on to day 19 then. Oh yeah, this problem... For this problem, there wasn't really anything too interesting we could do. Part 1 was basically just an implementation. Not a simple one, but definitely a relatively straightforward one. You basically just input exactly as the problem statement describes. Part 2 is the interesting one, but even this was basically just involving ranges, and you basically just to make your function, instead of taking in specific xmas values, it just takes in ranges of values and then just splits them up and sees which ones pass and sends them to different workflows as a result. Let's just re-implement this. So how is this done again? Right. And then for the workflows, let's implement this with classes to see if we can make our code look a bit nicer. So for each workflow, we'll have the workflow won't need to know its name because we'll store that in a dictionary of workflows. But each workflow will need a bunch, basically just a list of rules. So def init, it'll need to take a list of rules and a default. And each rule will be, it'll need a parameter, which will be one of X, M, A, or S, a comparator, or actually we can generalize this to just have a function to determine whether or not it passes. Thanks. What's this problem called? Aplenty. Each rule we can just give it a predicate. So a predicate is just a fancy name for a function that basically just returns a true or false value. It'll take a predicate and it'll have what's it called? The name of the workflow that it sends it to. So we can call it target, I guess. And now to take in all of the inputs for line in a.split lines, this gives us all of our workflow rules. So the processing for it is going to be name is line.split on open curly bracket to the left, and then the rest will be, we can just do name rest equals this. And then we can also chop off the last character here to get rid of the right curly bracket. So now we have this. The name is on the left and the remainder is on the right. And so then we just need a function to construct a workflow. So we can do def construct. And if we don't pass it self, instead of being an instance method, it'll be a class function, meaning we can just call it on the class. And so def construct from string. str is a bad name. Construct from S, I guess, we'll take star rules default equals s dot split on comma, and then for each we'll do return workflow. And then we'll need to parse these rules as well. So what we can do is we can also make a construct function for the rule class. And then we can return rule.construct rule for rule in rules.split. Rules is already a list. And then for the rule constructor, we can just say predicate target equals s.split on the colon. And so predicate will be this part and target will be this part. And so now we just need to convert this into a predicate function. And so I guess to generalize this, what we can do is we can require a function to be passed to the constructor that tells us how to convert a string into a rule. So I guess we can call it rule factory. And then we'll pass it into, this is definitely over engineering, yes, but it's I feel like it's kind of pointless to just re-implement what I did in the video exactly. So yeah, it is definitely over engineering for an AOC problem, but I think that's fine. And then we can just return a new rule where the predicate is, we call the factory on the predicate description, and the target is just the target string. And so now we can just say workflows name equals workflow.construct rest. And then we need to give it a factory, so we'll def rule factory s is just going to be return. The key is going to be the first value in s. The comparator is going to be the second value of s. And the number is going to be the remainder of s. And so if the comparator is the less than symbol, we can just return an anonymous function that takes our object, which, what were the objects called again? Parts. Yeah, that takes a part and checks if the key for that part is less than num. So if you're not familiar with this syntax, this is Python's way of doing anonymous functions. Lambda defines a function, and these, you can give it arguments the same way you can give arguments to a normal function. So you can also have like rest arguments, keyword arguments, you can have default values, etc. And so this just takes in a part and returns if the key value of that part is less than num. And note that this is what's known as a closure in functional programming terms, because although key and num are defined within this function, this lambda can be returned out of this function and used, and these values will basically just become encapsulated in this. And if CMP is equal to greater than, we can return a greater than check. And if we reach this point, we just want to error. So then we can give it a rule factory. And now we should get a bunch of workflows. And so let's just check one of the random workflows. Its rules, its default is going to be whatever was at the end. So for PX, yeah, the end was RFG. And then if we print out each of its rules, we get a list of rule objects of length 2, which is what we expect. For the first one, its predicate. We can't really inspect this, unfortunately, but the target we can see is QKQ as expected. And now we can go through each of the lines in B. So for line in B.split lines, we have that. So in order to get that into a part, we basically want to take the line, we want to get rid of the curly brackets, and then we split it on comma. And now we want to convert this into a dictionary of values. So what we can do is, for each component of this, for item of this, we can do item.split on equal sign. Sorry, that's JS syntax. And then we can call the dict function on this, and it will turn it into a dictionary. The dict function is able to take a list of pairs, and the first item of each pair will be turned into the key, and the second item of each pair will be turned into the value. And now we just need a function to process the workflow. So what we can do is we can define the function within the workflow. So def process part. This one needs to be an instance method that takes in itself. And so we can say for rule in self.rules, if rule.predicate, so if the rules function applies to the part, then we return, we also need to give it the map of workflows. So return workflows rule.target.process the part. And if none of these apply, then we just go to the default. So return workflows self.default dot process part workflows. And this currently will not work. So if we try to print like workflows in dot, that was the start, right? Yeah. Dot process part. You don't need a static method. It might be better to do so, but it works without it. If we try doing this right now, we'll get oh. Yeah, sure. I forgot to turn this into integer values. So I guess let's do it this way. For item in line 1, -1 dot split comma kv equals item dot split equal sign, and then part k equals int v. If we try doing this right now, we'll get a key error because we haven't defined the R and A workflows. So what we can instead do is we can define a function to send the part to another workflow. So def send self part target. And by default, it'll just do this. Like so, and then we can just say if the target is equal to R, we return 0. And if the target is equal to A, we return... What was the value we wanted? The sum of all of the values. Return part sum of part.values. And now this should work. And so we'll get a 0 if the part gets rejected, and the value if it gets accepted. And so now we just track the total, and we just do total plus equals workflows.process. And that gives us part 1. So there is one thing I wanted to demonstrate here. So the main reason I did, sorry, wrong keybind. The main reason I did this over engineering is basically just to show that this makes the code a bit more structured. It is technically over engineering. But the other thing I want to show is that there's actually an issue with making your code more structured for AOC problems, which is that for part 2, this code is kind of difficult to extend because it's very rigid. However, there is also an advantage to this, which is that because we've separated out most of our concerns quite well, it becomes not necessarily easier, but a bit harder to mess up. At least in my experience, you might find this to be completely different in your case, but at least for me, whenever I do projects, which ultimately is, in my opinion, more important than competitive programming, separating out my concerns like this is definitely really helpful, because when I want to make modifications later, it's easier to pick out which parts need to be changed, rather than having to go through basically my entire code base to track down everything that is intermingled together. And so, yes, ultimately for a contest problem, this is over engineering. But in terms of code style for larger scale projects, you could consider making your code more like separate, basically, is what I'm trying to get at. So the reason this isn't extendable is because predicate here we've made an abstract function, and so we have no way to inspect it, so we can't just change this part or change the process part. And so what we're instead going to need to do is rely a bit more heavily on the input format. So we're basically going to need to make our code less extendable because we need to depend on our input being numerical and all of our comparators being being less than or greater than comparisons. So let's start from the top and work our way down. So first of all, we no longer need B because we're no longer processing anything. And so we basically want to get rid of this entire section. And so now we're trying to see how many possible distinct combinations will be accepted. And so instead of process, we'll want a function that can return the count. And we'll do this, we'll figure that part out later. But basically what we want is some sort of count function that we can just print workflows in .count. And so what do we want count to accept? Like with previously, count is going to accept the workflows object because we don't want to reference a global object from inside of a class. But it also needs to accept the current range, basically. And so for the range, we will simply represent it as a dictionary. And so it'll just be k to 1 4000 for k in Xmas. And so this will just create a dictionary such that for each key in X, M, A, and S, we get a range from 1 to 4000. And we'll make it inclusive on both ends. And so now what we need to do is we need our rule, instead of having a predicate, to be able to split into a true and a false side. So it'll still keep its target, which is its own value, but then instead of, for the predicate, we'll need a separator. We can keep the rule factory, and instead of predicate, what we'll do is we'll have our function accept the range and then split it off into two different ranges. So we keep our key CMP and number. And now basically what we're going to do is we can define an inner function that takes a part, and then we can return this function, because in Python functions are objects. And so you've seen me use this with like map into line.split. For example, this is the same logic. Int is a function. Technically, I think it's a constructor. And since functions are objects, you can just pass it in to a different function like so. And of course, you can also return them from functions as a result. And so now what we can do is we want to split it into a true range and a false range. And we'll make it return none if there's nothing on that side. So given the part, if our comparator is less than, then our true range will be part key 0 up to part key sorry, not part key, it'll be up to the number. And in case number is less than, no, greater than, we'll do min of part key 1 with the number. And then for the false side, and sorry, it should be number minus 1 because it's strictly less than. For the false side, it'll be the max of num and part key 1, no, 0, up to part key 1. And so I think in my video, I think I might have missed this min and max part. The reason we want that is just because in case our input range is like 1 to 10 and our comparator is less than 20, we don't want our true range to be 1 to 20 because that means that we'll get an output that's way too high. And so we want to make sure that our true and false ranges do not exceed the original range. So I learned coding mostly just through experience. Like, I wouldn't necessarily say I'm that, like, it would be inaccurate to say I'm not a good programmer, but it's not because I just learned really quickly or I'm really smart. I've just been coding for over 10 years. That's basically all there is to it. I am in university for computer science though, but most of my coding was self-taught. Like I didn't go through too many courses. It's mostly just competitive programming experience. That's where I got most of my coding experience from. And then if CMP is greater than, then the true range is going to be everything starting from num plus 1, and then the false part is going to be everything before it. Like so. Yeah, university, you do spend a bit of time coding, but the main component that you're really learning is like algorithms and I guess general problem solving, like how to approach computational problems. There are still courses where it's almost strictly just learning code. Like we did have some courses on like introduction to what was it called? Like I forget what the course names are, but we did have some courses where basically it was just teaching us exactly how to write code. But the parts that I think I learned the most from are the ones about data structures and algorithms. Because I think coding is easier to learn on your own, but the higher level topics are probably a bit harder, at least in my experience. Again, it differs for everyone. Yeah, calculating complexity and efficiency is definitely an interesting topic. I actually have a video that is already done. I'm going to upload it in the upcoming week about time complexity. I got into coding. Okay. So I got into coding basically just because I don't even remember. It was too long ago. My first experience coding, I think, was with Scratch, like MIT's drag and drop thing. I forget if we played around with it in school or if I went to a like program in my city that introduced us to it. I think that was my first experience with it, and I found it pretty fun. I tried Python for a bit, but I didn't really stick to it until sometime in grade 6 when my parents got me a book from the library about coding in JavaScript using the 3.js library, which is a 3D rendering library for JavaScript. And I think that's when I first got interested in it because I was able to do cool stuff and basically just turn ideas into like things that I could actually like mess around with. And then not too long after that, in middle school, I started doing the Canadian Computing Contest, which is our nationwide contest. And so after that, I've just been coding ever since then. So I learned shoelace formula a long time ago, but forgot about it. The reason I remembered shoelace formula for day 18 is actually because of day 10. So I didn't think of shoelace formula for day 10, but someone in my YouTube comments mentioned the idea, and I didn't even understand it at first, but I thought about it some more, got some help from some people on my Discord server, and so ultimately the only reason I was able to use shoelace and picks on day 18 is just because people introduced it to me on day 10. Yeah, getting introduced to coding early definitely gives you an advantage, but it's never too late to start. Anyway, we're going to want our rule factory. We're going to want the separator to return two parts. So the contract for this function is basically return a true part and a false part. And if either side is empty, we want to return none. So we'll transform both of the parts. So if t0 is less than or equal to t1, then it's not empty. Otherwise, we'll set it to null. Or none is the Python version of null, basically. So in order to transform this, we'll need to do t equals kv for kv in part.items. This just part.items basically does the inverse of what we did earlier with our dict function, the one that I removed eventually. Instead of taking a list of pairs and transforming it into a dictionary, this returns an iterator over the pairs of key and values. So that's where this comes from. For each key and value, if if the key is equal to the key that we used as our separator here, we're going to feed it t. So t if key, k is key, else v. And so basically what this is doing is, I think this might actually be a bit simpler. If we call the dict function on part, it just clones it into a new dictionary, and now we can just mutate it. And it occurred to me I shouldn't be overwriting my variable names. The true part is going to be a copy of part where the key range has been substituted for t. And we'll do the same for f, where the false part is going to have the key value substituted with f. And so now if we feed it a range of like x is 1 to 1000 and our comparator is 500, t part will have the m, a, and s values as the same range, but x will be substituted with the 0 up to 499, and f part will be the same as the original part with the same m, a, and s values, but the x value will be substituted with 500 up to 1000. And so then we just return the true part and the false part separately. We could also extract this into a function to avoid duplicating the code. And so now if we construct the rules, we should get a bunch of rules with their individual separators. And so now we will need a count function instead of a process function. So for each rule in self.rules, we will say t part, f part equals rule.separator on the part. So we call the separator on the part and we will get the true and the false half. If the true half is not empty, so we'll want to keep a total here. If the true part is not none, then we will want to process it and we will pass it off to the rules target. So anything that passes the rule, so t part is basically every subset of part that passes the rule, we will send it to the rules target. And if the false part is not none, we will update our current part. So this iterator will basically just keep updating part until we eventually run out of stuff. Part equals f part. And if it's empty, we break. And then if we don't break, which we can use the for else syntax for, sorry, this shouldn't be a return, this should be a total plus equals. We will do total plus equals. We will send the remaining part that failed all of the rules. We'll pass that into the default value. And so now we just need to deal with the R and the A handling. So let's take a look at what our output should be. Figure out how many will be accepted. So if it's R, then all of these are rejected. So we return 0. And if it's A, we want to return the number of values that would be accepted. And so for each axis of part, so for each of the values, we take the range and we determine the number of values in that range. And then we just need to take the product across the x, m, a, and s values. So for example, if there are 2 possible x values and 3 possible m values, that gives us 6 if we just consider those 2 values. And so we can say total equals 1. 1 and not 0 because we're taking the product. And so we need to start with 1. And then for range start, range end in part dot values, we just multiply total by RE minus RS plus 1. The plus 1 is because our range is inclusive on both ends. And then if it's not one of the special case workflows, we just pass it back to this target and we call the count function. So I'm willing to bet this won't work first try because it's kind of hard to write code that works first try. Okay. So unsupported operands for plus int and none type. Okay. Yeah, I forgot to return the total. Cool. And that gives us part 2. I was so close to getting it first try. I just forgot to return the total out of my function. Yeah, so for this part, we've managed to keep most of the separation of concerns intact. So our rule factory, we still have a separate function that takes in our string and returns the required thing according to the contract. By contract, I just mean given the input, the output needs to be of a specific format. Python is actually a terrible language for this because of its relatively the type system isn't built into the language. There is a type system. Actually, it might be built in after a certain version of Python, but compared to other languages, the type system is not strict, and so you'll just get some IDE warnings. In type-safe languages like Kotlin, which I might actually use next year, you can make your contracts a lot more strictly defined. You can basically just say rule factory needs to be of type function that accepts a string and returns a function that takes a part and returns a pair of parts. You could define that strictly, and then if you try to give it anything else, you'll get an error. So there are advantages to using type-safe languages, but just like with this over-engineering, it's more useful for larger scale projects, and not for like quick scripts for competitive code. Okay. And so we still have the rules factory as a separate thing. We've renamed process to count, but we've still kept it separate where this part just processes its own workflow and everything else is sent through this function, which handles the default R and A values and then returns it back. Otherwise, I have not tried Project Euler, but I've heard a good amount about it, so maybe I will try it sometime. And then instead of predicate, we just have a separator that splits our parts into two parts. C++, yeah, so I'm not going to use C++ over Kotlin because C++ is a pain to use. Also because I don't feel like dealing with memory errors in AOC. Okay, we're a bit behind schedule, so I'll try speeding things up for the next few days. Oh yeah, pulse propagation. So I'm just going to skip any problems where there's nothing interesting beyond what I already showed in the video, actually. But pulse propagation, we do have something interesting to show. So for this problem, we're actually going to solve this without using any code. Rust, yeah, so if I learn Rust before next year, then maybe I'll use it for AOC, although I think Kotlin is actually still easier. But yeah, Rust, not for AOC. Rust, I'm considering learning it for project work because it just seems like a really nice language. But for AOC, it's similar to C++, in that it's too slow to write. Not that the languages are similar, but the main thing about AOC is I don't want to write maintainable code. I want to write code that works fast. And so that's why I'm not using C++ as well. Okay, we're going to try solving this without using any code because I think that's interesting. So part 1 is not that interesting. It's just a simulation, and so we're not going to look at part 1. But for part 2, if we take a look at the input, let's load it. We're going to output this in a format that lets us look at it in a graph viewer. Let's see. Can network X visualize graphs? It can. Cool. So we're going to import network X, which is a graph/network theory module for Python. It's not part of the standard library, so if you want to use it, you'll have to use pip install to get it. I used it for day 25 in my video. So how are we going to get our graph into this format again? Can we do it like this? Add edge. So left right equals line dot split on the arrow. And then we can do g dot add edge from like that maybe? No, because we need to do for v in for each target in r dot split on commas. We can do g dot add edge from L1 to R, sorry, to T. I don't know if this will work. Where is this failing on? Oh, because I'm running on the wrong input file. G has no attribute draw. Do I need to import a different library as well or something? Have any of you guys used NetworkX for visualizing graphs and stuff? Because I'm not familiar with this library. Oh, it's no module named matplotlib. Am I supposed to see it? Maybe it's because I'm using WSL. Will that fail to render or something? Maybe I'll just go pull up somebody else's graph. Give me a second. I'll be right back. Okay. Yes, I think I have a general solution for day 25. Anyway, so this is a graph that I stole from someone else. So the idea behind this is that we can determine the cycle length of this using binary, basically. So let's revisit what we're doing here. So Rx needs to receive a low pulse low pulse. In order for Qt to return a low pulse, these each have to emit a high pulse. And these are flip-flops, so in order to return a... Sorry, no, they aren't high flops. They are conjunctors. So in order to emit a high pulse, they need to receive a low pulse. So basically, we're looking for the first cycle in which these four all return a low pulse. So let's look at what happens. Each time we press the button on the broadcaster, it sends out a low pulse to this. In order for this to emit a low pulse, all of its inputs need to be high pulses. And these are all flip-flops in these circles, in these circular rings. And so XF, when it receives a low pulse, it will turn off. Sorry, it will turn on and send a high pulse, which will be ignored by this. It will also send a high pulse to this, but none of the other ones are high yet. Then once this receives another low pulse, it will turn off, and when it turns off, it emits a low pulse, which toggles this and turns it on. But because it sends a low pulse here, when this sends a high pulse, this still doesn't activate. When it receives another low pulse, it turns on. So let's write out our digits. So we have XF, MB, BQ, TJ, QD, DG, VM, GM, QS, JF, DN, and RB. When we send a low pulse, this turns on. Then when we send another low pulse, this turns off and turns the next one on. Then when we send a low pulse, this turns on. Then when we send another low pulse, it turns off, toggles this one as well. So when it turns off, it turns this one on. Perhaps this looks familiar because now we're just counting up in binary. So each time we send a low pulse, these values here, the ones in the ring, just keep counting up in binary. And so this will activate when it receives a high pulse from all of the ones that feed into it. So in other words, for each node that feeds into CR, it must be on. So it must be a 1. And so the number of times we need to press broadcaster for that to happen is just the binary value of this. And so if we look at which ones feed into it, we have 1, 2, 4 is not, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. And so we can just add up which ones feed into CR, and that tells us the binary value that we need to achieve. And so that will be the number of cycles it takes. Now, because of these outgoing values, it's also true that after that happens, after this emits a high pulse, it will reset the state entirely. So how do we ensure that? Well, at the end of the cycle, when all of the points have been reached, all of the ones that feed into CR will be on, and everything else will be off. And so CR, when it receives a high pulse from all of its inputs, will emit a low pulse. The low pulse will toggle all of these. Why does my eraser not work? Okay, what just happened there? Okay, so when CR sends out a low pulse, it will toggle all of these 0 values into 1s. And so now everything is a 1. And finally, it also sends a signal up to XF, which will toggle this back to 0. And every time a flip-flop is toggled off, it will emit a low pulse. And so this will propagate all the way around, and it'll turn all of them off. And so immediately after CR emits a high pulse, it will turn immediately after CR emits a low pulse, which causes KK to emit a high pulse, it will turn all of these values off, and then immediately emit a low pulse again. A high pulse again, which will cause KK to emit a low pulse. So basically, all of these must emit high pulses at the same time. Otherwise, immediately after it emits a low pulse, it will emit a high pulse again upon resetting everything. And so this ensures that the number of cycles needed is actually the LCM of the cycle lengths. So this problem setup is actually extremely clever. I do dislike the assumptions that it requires. However, I think I'll give this problem a pass because the binary setup of this problem is just too elegant to hate on. I did not think of this myself. I don't quite know who to credit. It's probably someone in the AOC Solutions mega thread for this day. But yeah, that's basically how you can do this without using any code. It is quite tricky to observe. This took me, I think like half an hour to an hour of someone else explaining it to me for me to fully understand exactly what I was doing here. But to revisit, basically, each time the broadcaster sends out a value, because of this chain of flip-flops, it counts up in binary. And the first time it validates CR is when all of the inputs become 1. And so that tells us the cycle length. And then when CR emits a low pulse, it will reset the entire cycle back to all 0s. And then QT will receive a high pulse from each of its inputs, only on the cycle where all 4 of these activate at the same time. And so we use LCM, or in this case, the inputs seem to be prime for everyone, so it seems like you can just take the product, but there's no need to make that assumption. We can just use LCM. And then the first cycle that happens, these all emit lows, so these all emit highs, and when Q2 receives all high pulses, it sends a low pulse to Rx, which gives us the answer. So yeah, technically you actually don't need a single line of code to solve this, although technically you probably do need some code to be able to visualize the graph this way. But yeah, that's a clever way of doing this day's problem. It also just occurred to me that my stream topic is out of view. Yeah, the reason I put it to the left side is because that way if I change the length of it, it goes to the right, but it's better to not block off code, so I'll just leave it on the right side. Okay. Let's see, moving on to day 21. Yeah, so there's a solution for day 21 that I wanted to go over. So we'll skip part 1 because there's no more clever way to do it than just flood fill. But for day 22, for part 2, what we can do is we don't need to rely on the geometric properties that I went over in my video. There's a way to solve this using quadratics. The idea is that assuming that the propagation rate in all 4 directions is roughly the same. So basically what we're assuming is that as time passes, the region that we can reach each time we increase the steps by a certain amount will be the same speed in all 4 directions. That's the important part to this. This works as long as there is an empty row and column in the grid. It's not a requirement, but it is sufficient. And so this means that this solution will actually work for the test input as well, because there is an empty row and column around each side. So what we're going to do is we're going to start by seeing how many points we can reach within a step count of total steps modulo the length of the grid divided by times 2. So what we're going to do is we're going to let f be the number of points we can reach with a step count of x. We start with f of some value x. Then we do f of x plus the size, 2 times the size of the grid. The reason we do 2 times the size of the grid is because the grid is potentially odd in width. It is for my input. I think it is for everyone's input. And so we need to account for parity because the number of steps that increases will be different each time. It will alternate as we expand our range because the grids will be opposite in parity. Then we check f of x plus 4s. Then we check so on and so forth. And because our area is increasing, eventually, if the propagation rate is the same in all directions, which it is for both our test and real inputs, then this function will approach a quadratic. And so we can then use that quadratic to extrapolate for x plus 2 times some number times s, where x plus 2ns is equal to the number of steps that we want. And so we want to start with x equal to the number of steps that we want modulo 2s. So in order to do this, let's just pull our solution for day 21 P1. Okay, so we'll be able to keep a large amount of this. So we have our grid, we have our start position, and then we just need to move this into a function. So def f of x, where x is the step length. We can do that. And to save a bit of time, we're not going to recompute at each stage. So I think what we can do is, how do we do this? we count up instead of down, I think. So 0. And then if s is equal to x, we continue. And the answer will be if s plus x mod 2 is equal to 0. So if s and x are the same parity, instead of if s is even, then we will add it to the answer set. And so then we can move can we do this? In the interest of time, let's just make our runtime a bit slower and just not cache the values in between. Okay, so if we return the length of answer here. If we print f of 64, this should give us our answer for part 1. Let's see, 42 for the test and 37 for the real answer. Yes, that's correct. And so now we want a step count of this. So now we can just do printf of steps mod 2 times size. So that will be our starting x. So then we'll just do while true printf of x and then x plus equals 2 times size. And also we'll need to modify this a bit. So currently it's checking if it exceeds the size of the grid. We want to get rid of that and just check modulo size. So let's move this up to the top. Basically what I'm doing here is allowing it to wrap off the edge of the grid. So if nr mod size and c mod size is # or nr and c isn't seen, then we continue. And so that also didn't seem to work. Oh. Yeah, so it does slow down a bit, but oh, yeah, so if you're using a different language, very important to note about #. Thanks for bringing that up. Sorry, this is the modulo operator. Thanks for bringing that up. So in Python, what happened to my terminal color? In Python, why is it still printing in blue? Okay, whatever. Just ignore that. It's just part of my utility script. So in Python, if you have a negative value, you'll get a positive value if you do this, and you'll get a negative value if you do this. So the result of modulo will be equal to the sign of the right side. If you do this in JavaScript, you get the sign of the left side. So very interesting difference and very important to keep in mind the difference. Python, you get the sign of the right side. JavaScript, C++, probably most other languages, it's the remainder operator and you'll get the left-hand side. So just an important thing to keep in mind. Okay. Maybe it is quadratic from the very beginning. I'm not actually certain. But the key point is that this eventually approaches, or is originally from the start. Basically, at some point, even if that point is the start, this relation becomes quadratic. And so by quadratic, we mean that we can represent f of x as ax squared plus bx plus c for some constant values of a, b, and c. So how do we determine this? We look at 3 consecutive values of f of x. So we have f of x plus 1, f of x plus 2. And the first differences will be different. So this will be difference 1 and difference 2. And then, sorry, we need to look at 4 values. These are the first differences, and they will be different. Then we'll have the second differences. And for a quadratic relation, the second differences will be equal. This is basically the rate of change. It's like the acceleration, which for a quadratic function will be a constant. So as soon as those are the same, we now have our second differences. And so let's just see where we arrive here. So a equals f of x plus 2s, f of x plus 4s, f of x plus 6s. Or let's do it this way. A equals this. While true, a dot append f of x, and then x plus equals 2 times size. And I will say if a has 4 items, then we will check if the second differences are the same. So the first differences are going to be y minus x for x, y in zip a1. This here just takes a and a but offset by 1, zips them together, and then iterates through all of the pairs. So this just gives us the consecutive overlapping pairs. So those are the first differences. And then second differences are y minus x for x, y in... Or actually, we can just hard code this like this. This is probably a bit easier. a1 minus a0, a2 minus a1, a3 minus a2. And then the second differences are fd1 minus fd0, fd2 minus fd1. If the two are equal, we break. Otherwise, we can pop the first element off A, so we're never keeping track of more than 4 items at once. And so eventually this will terminate, and we will get a second difference value. So those are the second differences, and those are the first differences. Okay, so now that we have our values, we can derive these originals. So we have 4 values of f, and let me think for a second. Actually, we're going to make it so that f is not a function from the number of steps, but rather an arbitrary intermediate value. We're going to make it so that f of x is equal to the number of points that can be reached, where the number of steps is equal to the original value plus 2s times x. So x is basically going to be the number of expansions that we did. So the original is going to be steps mod 2s, so we're going to call that original. And f of x will be original plus 2 times size times x. And so now instead of f starting at x and going up by 2s each time, we'll just start x at 0, and x will go up by 1 each time. And so now if we print out x, we know that, okay, so 6 is the next value we would compute. And so this is f of 5, 4, 3, and 2. And so in order to figure out what we're basically looking for f of the number of steps divided by 2 times size. That's the value we're looking for. And so now that we've found f of 2, 3, 4, and 5, so f of x is equal to, let's call it alpha, f of x plus 1 is equal to beta, f of x plus 2 is equal to gamma, and f of x plus 3 is equal to delta, then we can use this to determine the values of a, b, and c. So I don't actually quite remember how to do this. So if we take the if we take the difference between these two values like so, we'll get ax plus 1 squared plus bx plus 1 plus c minus ax squared plus bx plus c. So the c's will cancel out, and we'll get a of... So this will be x squared plus 2x plus 1. So when we subtract the x squared, we'll just get 2x plus 1 plus b... and the x's will cancel out, so we just get plus b. Then if we take f of x plus 2 minus f of x plus 1, we will get a of x squared plus 4x plus 4 plus b of x plus 2 plus c minus a of x squared plus 2x plus 1. This is still way too complicated. Oh, yeah. Thanks for the tip, Clement. Yeah, if we do x equals 0, this becomes a lot easier. Okay, so we're going to change our offset, basically. So once we have found this value, 6 is the next thing we're going to compute. So we're going to redefine the first value to x equals 0. So we're going to set the offset to x minus 4, because x is the next value we're computing, so we have 5, 4, 3, 2. So we're going to set the offset equal to 2, which in this case is x minus 4. Okay, and so if we have 0, then we have f of 0 is equal to some value alpha. In other words, a times 0 squared plus b times 0 plus c is equal to alpha, and so we just get c equals alpha. You could put the numbers into Wolfram alpha too, yes. Okay, so c is equal to the first value of a. For f of 1, we get beta. We have a times 1 squared plus b times 1 squared plus c is equal to beta. And so we know that a plus b is equal to beta minus c, which we already know from above. And finally, f of 2 is equal to gamma. We have, I don't know if this is how you draw gamma, by the way. We have 4a plus 2b plus c is equal to gamma. And so we have 4a plus 2b is equal to gamma plus minus c, or 2a plus b is equal to gamma minus c over 2. And so now we can combine these two together. We get, if we take the difference of the functions, we get all a is equal to this minus this. So it's y minus c over 2 minus beta plus c. Or if we rewrite that a bit, we get y minus 2 beta plus c over 2. And then b is equal to double the second 2b minus this thing, because that way we get 2a plus 2b minus 2a plus b. So the 2a's cancel and the 2b minus b gives us our b value. And so it'll be 2 beta minus 2c minus gamma minus c over 2. And we don't have to rewrite this, I think. So c is a0. So let's just do this. Alpha equals a0. Alpha, beta, gamma, underscore equals a. And now we can just derive our formula. So c equals alpha. A equals... Actually, we can do this a lot more simply. B just equals beta minus c minus a. So once we get a, we can compute b really easily. So a equals gamma minus 2 beta plus c over 2, and b is equal to beta minus c minus a. And so just to confirm that we're not, just to sanity check this, we'll redefine f of x to be ax squared plus bx plus c. And these values should line up. Shoot, I overwrote a. Let's call these values. And just as a sanity check, we should get the same thing when we look at these two values. And they do line up. Perfect. So now we just need to take our offset, and we just need to take print f of the number of steps divided by 2s minus the offset. And wow, that actually works. It does take a bit of time because filling up these values does take us a bit of time, especially because I didn't bother optimizing this. But This is a much more clever solution than what I had. My solution was really complicated with like taking the corner cases, the small and large, what's it called? The inner and outer edge cases, and then like computing the area of the inner section. This solution by comparison is a lot more elegant. Basically what we do is we observe that as the area grows, our relation between step count and number of reachable positions is quadratic. And so we can just directly obtain the quadratic relation mathematically and then just redefine our function and compute it mathematically to instantly get the answer. So a very nice solution. This does unfortunately mean that we cannot get values that are arbitrarily in between, but to be fair, neither could my solution. And this one is, by comparison, a lot more general case because it does also work on the test input. Albeit, for some reason, we're not given this value in the test input, so we can't even test our solution. Anyway, moving on to day 22, sand slabs. It is quadratic for all offsets? Oh, so could we have fed in... I guess in that case, we didn't even need to skip by step size each time. Wait. No, that's not true. We can compute it for all offsets. It's just that we would need to change the step size offset between runs. So I guess we could still test it on the test input. Yeah, you're right. Okay. Let's look at this one. Was there anything clever for this problem? I think there definitely was. Okay, yeah, so it does work for the test input, actually. We just need to change this number. My bad. Yep. It does actually work for the test input. Okay. Moving on to day 22. One optimization that people observed is all of the bricks are relatively small. They are up to 10 cubes. And because they are only long in at most one direction, each brick only has up to 10 xy coordinates that exist in it. And so instead of range checking, it's actually faster if you just check every single coordinate within the brick. And so if we do that, let me think about this for a second. Okay, so for part 1, let's grab the test input and the real input first. For part 1, I think what we can do is we can basically just look through every coordinate that's covered, and only the topmost brick in that coordinate is marked as valid. And then for any brick where all coordinates are marked as valid, it's at the very top and there's nothing above it, and so we can safely disintegrate it. I think that works. Let's see. So we'll have a set of coordinates that we need to check. Actually, we'll make the coordinates a dictionary pointing to the topmost brick. And then for each brick, so for line in open 0, x1, y1, z1, x2, y2, z2 equals line dot replace the tilde with a comma dot split on the comma. And then we'll also need to keep track of each brick's span, basically. So the span of the brick is going to be the range of the x coordinates times the range of the y coordinates. And since they're inclusive, we need to add 1 to each. So I'll quickly explain what I'm doing here. So basically, for the first brick, it covers 1, 0, 1, 1, and 1, 2. So if we look at it from above, it'll cover 3 coordinate spaces. So all 3 of these need to be unobstructed for A to be disintegratable. This one also covers 3, and... Wait, this doesn't even work. Never mind. Because I forgot that bricks can rely on multiple different bricks. We can still use this technique, though, to... What's it called? To determine the dependency graph of which bricks lie on which other bricks, I think. Wait, does this even work? Let me actually pull up my previous solution for this. I think we can make our solution faster is the main thing. Yeah, let's not waste time re-implementing the whole thing. Let's just see if we can optimize this solution a bit. So, where's the slow part? I guess maybe that part's slow. Okay, that takes about half the time, so it's not the only thing that's slow. Yeah, so we can keep a dictionary pointing from each xy coordinate to which bricks are in it. So we can say chords equals this for So basically for each coordinate that the brick covers, we'll do chords at xy dot append brick. And so since we're returning references to the bricks, if we modify them later on, it will update here because we're pointing to the original brick object. We're not making a copy of it. So basically, chords will now store a map from each xy coordinate to which bricks are in its position. And so then for index brick and enumerate bricks, instead of going through every single brick, we can just look at the bricks in the coordinate space. So for, I guess we can say check equal for check in. Since this check is fast, actually faster than doing set modifications, we're not going to do any set logic. We'll just deal with the duplicate checks. So for check in, we'll do for x in range brick 0. There's got to be an easier way of doing this. Let's define a function that gets the coordinates from a brick. return xy for x in range brick 0 up to brick 3 plus 1 for y in range brick 1 to brick 4 plus 1. Okay, this just saves us a bit of time, so we can say like for coordinate in get chords for brick. We can do chords c dot append brick. And then we can just say for c in get chords of brick, and then for check in chords at c. And so now this might speed it up a bit. It also gives us the wrong answer now. That's great. Oh, I think the issue is because we're checking the brick against itself. So if brick is not equal to check and overlaps. No? Wait, what is the problem with this though? This feels like it should be correct. Also, the fact that the value is so close is a bit suspicious. Wait, now I'm a bit confused. Oh, it's checking bricks that are above it, isn't it? That's probably why. We need to only check bricks that are below it. And so since the bricks are sorted, I think we can go up to chords c dot index of brick. I think this works. Yeah, and we can save a bit of time by saying if check equals brick, we break out of this loop. So we don't need to do an index check. Okay, yeah, so basically the problem with my initial solution was that I was checking bricks that were above the current one to see if the lower brick would fall onto the upper brick, which obviously doesn't make sense. And so yeah, instead of skipping, we need to break so that we don't check any bricks beyond that point. And this works because we sorted bricks here, and so the coordinate lists will also be sorted because we're going through it in sorted order. Okay, so that saves us a bit of time. And now here we can also say instead of looping through all of the bricks again, we can say for C and get chords of bricks for lower in chord C, if upper equals lower, we break. And otherwise, if they overlap, we... Oh, shoot. That's a bit of a problem. We no longer have the index mapping. Oh, that's fine. We can just do like... We can just define a dictionary, because at this point, we no longer need to mutate the bricks. So we can just do bricks equals map tuple. We can just turn them all into tuples. So now we can hash them, basically. And so we can just do IDs equals brick I for I brick in enumerate bricks. So now we've assigned each brick a unique numerical ID. And then we can just do I equals IDs of upper, and then here we can just do j equals IDs of lower. Oh, shoot. Can only concatenate tuple, not into tuple. For C and get cores of bricks. Wrong one, upper. Unhashable type list. Oh, because chords is still stored as lists, so we can also change chords to tuples now. So chords equals k list map tuple v for kv in chords.items. Okay, that is... That is very much wrong. I am curious how that messed up so much. Is it because the chords are no longer... I think it's because the chords are no longer in sorted order. We might need to just reconstruct it. Yeah, I think we just reconstruct it. So we can just reset chords equals... I think this is the easiest way of doing it. Nope, still doesn't work. Chords should now be in sorted order again. So... It works for the test input too, which means that it'll be impossible for us to debug it using the test. Let's do a bit of debugging on the test. So print bricks. So that's A, that's B, that's C, but it's fallen down by 1, that's D, but it's fallen down by 2. That's E, but it's fallen down by 2. That's F, and that's G. Okay, so they're still in the same order. And so now if we print out the support values, so if we print K supports V, we see that oh, these are out of order. Oh no, I see. So J, I got the values wrong. J was the ID of the upper one, and I was the ID of the lower one. Okay, there we go. And we can see that that runs way faster than the original solution. Yeah, so the key observation is we are no longer using our overlaps function. Wait, yeah, we can remove this. We are no longer using our overlaps function and instead just directly obtaining... Wait, what? We shouldn't need this, though. We shouldn't need the overlaps function because this is supposed to only give us bricks that overlap, no? That's really weird. Okay, so the first overlap check was unnecessary. Oh, it's because I removed this whole thing. My bad. Okay, so yeah, we do indeed no longer need the overlaps function. And so what we're doing is instead of checking all of the bricks and seeing if they overlap, we can instead store a list, store a mapping from every single XY coordinate of the brick to the brick itself. So then when we check each brick, we can just loop through each of its coordinates and look through all bricks that are stored within that coordinate set. This theoretically gives us a lot of duplication, and if the bricks were large, this would be exceedingly slow. However, because each brick only has up to 10 coordinates in the XY plane, this is much faster than checking through all of the other blocks. And so overall, this solution gives us a significant time advantage. It's also a bit simpler, really, because we no longer need to think about how we do the overlap function. We can just store all of the coordinates as a map. For part 2, we can also basically steal our original solution. And so basically the way we did it, so we just looked for each brick. If we tried disintegrating it, we use a flood fill to determine how many bricks will fall. I wonder if this is slow. If this is slow, we can look at a better way of doing this. Named deck is not defined. This is not slow at all. This runs instantly as well. So yeah, I'm not going to revisit part 2. There are other ways you could go about doing this problem, I believe, but this is fast enough, so in the interest of time, I'm going to move on. But basically, the main observation I wanted to present for this problem is that there aren't enough, the bricks aren't large enough to justify going through each brick. Instead, we can go through each coordinate and just directly have a map to which bricks are within those coordinates. Okay. So that's all that was really interesting for day 22. For day 23, a long walk. Oh yeah, it's this problem. So I forget, was there anything interesting for this problem? The main thing that we did it's not called edge contraction, it's called path contraction. So basically what we did here was we took all of the crossroads points, so all points where there's actually a split. So basically what we observe is if a point has only 2 neighbors, then there's nothing we can do at that point except keep walking in the same direction. So we can draw an edge directly between each of the crossroads points. And that gives us a much smaller graph, and then we just brute force because it's longest path and there is no... Yeah, longest path is an NP hard or NP complete. I forget which one's which problem, meaning that there is no efficient solution. In the general case, you basically have to brute force. Now, I guess one interesting thing to note is if we grab our solution from the original solutions. Part 1 was brute forceable, so I'm not going to bother going over it. You didn't even have to do path contraction for part 1 because of the lack of loops. Let's print out our our path contracted. I think this was our path contraction part. Yeah, so graph was the interesting part. So now let's try printing out our graph. So we'll have a list of IDs again. So IDs equals node I for I node in enumerate graph. And then we can for key in graph print IDs k, and then for k in graph, for v in graph k, print IDs k, IDs v. Okay, so if we grab our graph representation and feed it into a graph visualizer like the CS Academy one, the single path chains, I don't know how long they were actually. They aren't too long though, I think. If we go to CS Academy's graph editor, something we can note about this. So 0 is the starting position and 1 is the ending position. I'm not going to go through the code implementation because I really am unfortunately a bit short on time today. But sorry, this takes a while because the graph editor for this website is actually a bit clunky to use. But wow, this is really terrible. Okay, finally. What we can observe here is that we basically have a grid. So, of course, the corners of the grid are absent because they would get path contracted. Oh, can I fix points? Oh, I should have known about this a lot earlier. Okay. Wait, this actually makes things a lot easier. But yeah, basically what we observe is that our entire graph forms a grid. And this this is not necessarily the case. So like it is possible to make a graph on a grid in a maze-like format that doesn't follow this. For example, we could have like the 9 to 11 edge missing, but this happens to be the case for my input, and I believe everyone's input. Because again, this seems like too much of a coincidence to not be the case. So I'm not going to bother implementing these optimizations, but we can make a couple of interesting observations here, which is that because of the structure of this graph, we can preemptively terminate some paths. So for example, if we're at 29 and we go down to 31, we know that we must go right. Because if we were to go left, then we would get stuck and not be able to reach the endpoint. So in this case, I'm treating the start point as the top left. So, no matter how we reach 29, if assuming we don't reach 29 going from 31, let me actually move this to the whiteboard. So assuming we're not reaching 29 from the bottom, then no matter how we reach 29, if we go down to 31, then the left side is entirely cut off. So if we go to the left, we won't be able to get out without crossing another node, so we have to go right. And so this allows us to preemptively terminate some of our paths. Now, another thing we can do is I think we can use dynamic programming. Now, unfortunately, I still didn't quite understand how this solution worked. But the idea is if we are at a certain point and we have basically for each state before, each state will consist of a bunch of paths and up until we basically consider only the points before in the grid. So we go row first and then column. So now what we observe about this is if the node above is open, then we must connect to it. The reason being, if we don't connect to it here and then proceed to the next node, there's nothing that can connect to this anymore because we've already exhausted all of its available options, so it must connect down. This is actually impossible here, but whatever. Let me draw a better example. So let's say we have some example path up until point 13. I don't know if this is possible under our constraints, but let's assume it is. So now at point 13, we have two options. We can connect upwards and then don't connect left, or we can connect them both. And so what we essentially do is we keep a list of pairs, which are the start and end points of each subpath that we currently have. Then when we reach each point, for each state that we previously had, if the above point is open, we must connect to it, otherwise nothing will be able to connect to it later. If it's like this, for example, and it's closed, then we obviously can't connect to it. So we either connect left or we don't connect at all here. And then when we reach this point, let's say we connected left. Now when we reach here, we again have the option to connect up or connect to both left and up. And so we can use that. I think it is a bit more optimal. It heavily relies on this grid structure and allows us to take advantage of its specific format to save some time. Now, unfortunately, I couldn't get this working. I tried implementing it and it just didn't work. I wasn't able to figure out exactly how to get the solution working. But this is an option besides brute force, and it should be much faster. So that was the interesting observation I wanted to present for this problem. Beyond that, it's basically just path contraction and brute force. And so I'm not going to revisit that part of this problem. It's the method I used in my video already. All right, day 24. Day 24, I just did this one via abusing built-in standard distribution math libraries. I think there is an alternate solution to part 2 involving rotating the entire coordinate space such that all of the paths intersect at a single xy position, but I didn't understand exactly how that worked. So, did any of you guys have a solution for this problem that was interesting? Because I know there are other ways of doing it than just using a standard math library. Yeah, part 1 was relatively straightforward. We basically just used intersection of intersection of lines. And part 2, we just set up a bunch of constraints using SymPy. Yeah, the part 2 that I used was relatively uninteresting. We just import SymPy for each of the hailstones. We just add 2 constraints for the equations, and then we just tell SymPy to solve it for us. I think there is one thing we can do. We can add integer constraints, I believe. So I don't think I can get IntelliSense because Pylance can't detect the library, but if we look up SymPy integer constraints on variables, we can tell SymPy to assume things. Okay, so when we create a symbol, we can give it some assumptions. And so, for example, we can assume positive is true, which isn't what we want here, but does this work? Oh, I didn't steal the code into my solution file. Okay. Okay, so by assuming that the values are integers, I think we can actually speed up our solution by a bit. So if we don't assume that, nope, it's not significant at all. However, so what I was doing here was I was printing I, which is the number of iterations we had. So if I don't assume integers, we need to do an extra iteration. We need to add an extra set of equations. But if we set integer equal to true, then we only need to do three iterations. Because I starts at 0, so it's one more iteration than the value. So this does technically save us a bit of time, because I think this even speeds up SymPy's ability to solve. I'm not sure if it does, though. You do only need the first 3 particles if you are using integer constraints. But if you don't, you actually need more than that, I believe. Because you do have 6... My set of equations allows one of the coordinates of the rock to be equal to the coordinate of a hailstone. Is that a problem, though? Let's try with what you said, though. Assume that xr minus sx over vx minus vxr is equal to yr minus sy over vy minus vyr. And now if I don't set integer constraints. Oh, interesting. Wait, why does that change? Why does that change things though? Because I guess the difference is that now we avoid allowing this to be 0. So the rock's velocity cannot be equal to that of a hailstone. But why does that matter? Why is that not allowed? Like, I'm just not understanding why exactly we want to ensure that the velocity of a hailstone cannot equal the velocity of the rock. Because it's not the whole velocity, it's only one component of the velocity, right? And so I'm actually surprised that this doesn't cause there to not be a valid answer. Remember we isolate time to collision? True, but what if a rock starts at the same x coordinate as the hailstone and then moves at the same x velocity? Like, what's preventing us from having a hailstone that does this and a rock that does this? Then they have the same x starting position and the same x velocity. In any case, the main thing I wanted to show here was just that in SymPy you can set integer constraints. So that doesn't mean that you only need 3 rocks. And 3 equations, 3 hailstones. And in case anyone is wondering, since I do think somebody raised this, there are 6 variables. And someone was wondering, why are 3 hailstones not enough? Because we have 6 equations after using 3 hailstones. And the reason 6 equations for 6 variables might not be enough is in case the equations are not independent. So typically, you probably remember from school that if you have a system of 2 equations, then it is enough to determine the value of 2 variables. So in this case, we can uniquely determine that x is 2 and y is 1. But the thing is, if your equations are not independent, so let's say we have x plus y plus z equals 3, and x minus z is equal to 2, and 2x plus y is equal to 5. This is not enough to give us the value of all of our variables. And the reason is because this third equation is what we get from adding up these 2 equations together. And so these are not independent equations. Which means that basically the last equation isn't giving us any information. And so we can observe here that if we set like x equal to, what's a good example here? If we set x equal to 5, y equal to 0, and z equal to 3, this works. But if we set x equal to 2, y equal to 3, and z equal to 0, this also works. And so we see that we don't have a unique answer. And so that's the reason why 6 equations might not be enough, because those equations might not be completely independent from each other. There it is. Lastly, let's go to day 25. So let's go over the solution I mentioned in my video that I said I wasn't going to go over there. The idea is that if we repeatedly find the path between every pair of nodes, then we can assume that the 3 most commonly used edges will be the 3 that we want to remove. Basically, if we take the path between every pair of nodes, then those 3 edges will need to be used a lot because they are the only way to cross over the halfway point between the 2 components. I implemented this really horribly when I was doing this on contest day, which is why I didn't show it in the video because it was really slow. But it's because I forgot that BFS can be used to find the shortest distance from one node to all other nodes at the same time. And so I was doing an unnecessary amount of iteration. So let's try this solution. So we're going to need our graph. So graph equals this for line in open 0. Left, right equals line dot split on the colon. And then for node in right dot strip dot split, graph left dot append right, and graph right dot append left, and then we can set this to a default dict. So okay, so that I keep messing that up. So that gives us our graph. And now we can do BFS a bunch of times. So we'll keep track of the number of times each edge is used. So we'll do edges equals this. And then for node, for start in graph, we will how do we do this? Oh, right. We can just say for I feel like there's a more efficient solution than doing path backtracking a bunch of times. Anyway, let's try the straightforward method first. So we'll do Q equals dec starting from start, and scene equals the set containing start. And then we'll also need to keep a backtrack map as a dictionary. So for while Q node equals Q dot pop left, and then we don't need to keep track of distance because we don't care how long the path is. So then we can say for next in graph node if nx not in scene dot add nx, q dot append nx, and then we will set the previous of nx to ourselves. And so now previous will be a map from each point to the point that we used to reach it. So now to backtrack, we can just start from each node. So for node in graph, if node is equal to start, we can continue. Otherwise, we will backtrack through this So we will say while node is not start. Actually, we can just do this. While node is not start, we will backtrack. So nx equals previous of node. So now we have that nx was the node that we reached right before reaching our current node. So we just keep backtracking up until we eventually reach the start. And in the middle here, nx node is going to be the edge. So we'll do edges nx node plus equals 1. We can also set this to a default dict containing the value 0. And then because of the possibility of nx and node being in opposite orders, we will do the pair min nx node and max nx node. They're both strings, so we can get a total ordering. We can use min and max to sort them. And so now if we print out edges, we should get a count of the number of times it was used to connect two nodes. Now if we remove that break, we'll get a better count, and then we can sort the entries. Or rather we can, so we can do edges edges by uses equals sorted edges. So if you sort a dictionary, it just sorts the keys. And then we can use key equals edges.get. And so basically this sorts edges where the key that we use for sorting is the number of times it was used. And so this is it in sorted order. We can see that since it's sorted ascendingly, the last three edges are JQT-NVD, which is this one, HFX-PZL, which is this one, and BVB-CMG, which is this one. If we run this on the real input, it will still take a decent amount of time, but I think it'll run within a reasonable span. I'm not sure. Oh, yeah, that runs in a reasonable amount of time. And that gives us our three edges to split. So now we can remove those from the graph. So for A, B in edges by use, we can delete them. So graph.a.remove B, graph B.remove A. And now we just pick a random node and breadth first fill to find the number of nodes within the graph. So we can just do Q equals dec containing some random node. To get a random node, we'll just do how do we do this? Next. No, we can just do list graph at index 0. It's not actually random. It's always going to be the first node, but it does not matter which one we pick. That's the main point. And now we can just do the same BFS thing. It would be nice to have a BFS utility. I'll probably use a utility file next year to save some time. But this year I deliberately tried to not use one. Oh, sorry, deliberately didn't use one at all. While q node equals q.pop left for nx in graph node. If nx not in scene, then we do q.append nx and scene.add nx. And now length of scene will be one side of the graph. And then b will just be the size of the graph minus a. Because if we know the size of one component, we know the size of the other. And we see that our sizes are 6 for the first component and 9 for the second component. Again, the ordering does not matter, so then we just print a times b. And so although this is a bit slower than the NetworkX solution, it is nice to have a solution that we did on our own without using, just depending on a built-in library. And so that gives us our answer of 558,376. Okay, another idea for this one, random spanning trees. So a spanning tree is a tree that covers all nodes in a graph and is also a tree, and also only uses a subset of the edges. So basically we just remove any unnecessary edges, and any spanning tree must contain exactly one of the 3 bridge edges. And so if we keep taking random spanning trees, we should observe that the 3 most commonly used edges are going to be the 3 that we can remove. I'm not going to implement this in the interest of time, but if you want to look into into minimum spanning trees, that can be done using Prim's algorithm and also Kruskal's algorithm. There are different things that do the same task. Minimum spanning trees being a spanning tree that has minimal total weight. Of course, in this case, since the edges are unweighted, it doesn't actually matter. And you can do spanning trees by basically just repeatedly adding in edges that don't form a cycle. Actually, how much time do we have left? It's 4:30 my time, and I only have until about 5 to 5:30 or so. I think we might actually be able to try that method out. Okay. We're going to keep all of this. And then for everything else, we'll do a bunch of random spanning trees. So in order to check if 2 nodes form a cycle, we're basically going to keep track of which nodes are grouped together. And so let's suppose we have a bunch of random nodes, and I'm not going to draw out the edges for now, but basically what we do is we pick, we go through the nodes, the edges in order. And then for each edge, we check if it connects to nodes that are currently not connected. So for each node, we will assign it a root. And then each time we join two nodes together, we will set the root of one to the other. This technique is known as disjoint set union. And now we connect these two together. When we do this, we set the root of this one to the root of the other one. And now if we take a look at this edge, for example, we would see that the root of this one is equal to this node, and the root of this node is also equal to itself. So since the roots are the same, then we do not connect this edge. Basically, we are just keeping a bunch of rooted trees. There are two optimizations we can apply here, and we'll only use one. The first is we put the shorter tree under the taller tree to reduce the total height of the tree. The second is path compression. Basically, when we take a look at this node, if we want to find its root, we don't want to backtrack 3 times. So instead, as we backtrack, we'll flatten out the tree and set the root of all of these nodes to this one. So as we do repeated checks, eventually our tree will become 1 deep. And so that will save us a lot of time for our lookup. Okay, so let's define a function that gets a spanning tree. Def spanning tree. We will return a list of edges in the spanning tree. Or actually, we're not even going to return the list of edges. We'll just add it to here. So for edge, we'll need an edge list as well. So edge list equals, actually in this case, since we're doing edge list, we don't even need the original graph. So we can just do edge list dot append left right. Oh, we still need default dict. Wait, no we don't. Okay, and now each time we do a spanning tree, we first need to shuffle the edge list because we're trying to get random edges each time. So import random, we'll do for blank in range like 1000. We'll just do 1000 random spanning trees. Random.shuffle edge list, and then we'll do spanning tree, and then we'll see where we go from there. So each time we do a spanning tree, we'll say for edge in edge list. We need to check if it connects the nodes together. So we'll need a set of nodes. So for each edge and edge list, we'll do exactly what we described here with the roots. So we'll define a dictionary that points at each node's parent. And initially, each of the parents will point to itself. And then we'll define a root function that will take a node and determine its root. So if it is its own parent, then we just return itself as its root. Otherwise, we set its parent to the root of its parent and return that value. This is the path compression thing I was talking about. We could just recursively call return root parent of node, and basically that just finds the root by continuously backtracking. But we can add an extra layer of optimization by immediately taking this node and setting its parent to the root, and that way the next time we check it, we only need to apply one call and we don't need to recurse. It's basically like memoization, but it updates if this ever changes. And so it's important that we don't set it's important that we actually no, this can't happen anyway. So basically the key observation is that even if we compress this path to length 1, if this node ever becomes the child of another node, then when we check again, we will see that we will get a path of length 2, and then our compression will apply again. And so this will technically repeat the assignment each time, but that's not a problem. Doing an if check here would technically slow it down, and also the optimization does not matter. So for each edge and edge list, we add it if and only if the two endpoints are not already connected. And so if edge, we can say for A, B in edge list, if root of A is equal to root of B, then the two nodes are already in the same component. And so they are already connected. If they are not already connected, then we will need to update the parent of one of them to the root of the other. So we will do, if we have two components that are connected, so like this, for example, if we try to join two of these together, what we will essentially do is we'll move one tree under the other. And so we will take this one, we'll find its root, and we'll make it a child of the other one's root. And so we'll do parent of root A is equal to root of B. Now, we should define these here, so we can save on a computation. Now, the thing I was talking about with the height optimization is whether we assign the parent of RA to RB or the parent of RB to RA, the optimal method depends on which tree is shorter. So if we have a tall tree and a short tree, it makes more sense to move the short tree under the tall tree rather than the tall tree under the short tree, because that way we reduce. So if we have a tall tree and a short tree, moving this way would result in a tree that looks something like this, which is relatively short. If we move it the other way, we would get a tree that looks something like this. And so this tree would be deeper as a result. This tree is no deeper than before. However, this optimization really does not matter. I've never had any situation where this matters at all. So if you ever need to use disjoint set union, which is what we're doing here, don't bother with this optimization. It doesn't really accomplish anything. Okay. And so now if we use this edge, we just combine the two components. And then again, we need to increase this. So we'll do edges of AB plus equals 1. Maximum recursion depth exceeded in comparison. Oh, I forgot to return here. Whoops. Key error. Again with this error. Key error again. We are not. Oh, not all of the nodes are listed on the left side. My bad. Okay, so now we have all of the nodes. And so this should theoretically give us the same as before. So now we can just print. I should have deleted the rest of my code. But if we do edges dot sorted edges by key edges dot get, we see that the last three edges, are they correct? Or once again, HFX PZL, BVB CMG, and NVD JQT. And so if we take the last three elements of that, and then we do for A, B in sorted edges, graph A. Oh yeah, we need the graph for the BFS at the end. We can do edge list dot remove. Or actually, no, we can replace the edge list with sorted edges, where the key is edges.get, and then we only take up to the last three elements. And now we can do for A, B, and edge list. We can do graph A dot append B, graph B dot append A. And now this should work. And now we can just do our breadth first fill again. So for star equals for Q equals deck of start and cin equals a set containing start, and then we can just do while q, and then we should get our answer again. So 54 is correct for the test case, and yep, 558376. And you can adjust this number here as well. So the lower we make it, the faster it becomes, but the more likely that it'll be incorrect. The higher we make it, the higher the probability that it's correct, but also the slower it becomes. Basically, as we apply more random operations, we have a higher chance of the three bottleneck edges actually becoming the three most commonly used. And since this is a random algorithm, there's technically no guarantee that it will ever be correct. But as long as the number of times we run spanning tree is high enough, we should have a decent probability of getting the correct answer. And the larger the graph, the more runs we need as well. So yeah, I think I still prefer the first solution, but technically the first solution is also not guaranteed to work, I believe. So how much time? We have time to go over our last idea. So this is basically the network X solution, but without using a built-in library. So what we're going to do for this one is we're going to fix a start and end point and assume that they're in opposite components. This may not be the case, but we're going to assume it is. And if not, we will know that it's not. So this is not a random solution, it's guaranteed to work. So in network flow theory, if we imagine each edge is having a maximum capacity, what is the maximum flow that we can get from the start to the end? So let's assume that each edge has a flow capacity of 1. In this case, we see that we can only achieve a max flow of 2 because there are only 2 edges coming out of S. And then this would be a valid network. All of the other edges are not needed. Let's say we have this, for example. Where we have a bunch of nodes like this. And I think you can see where I'm going with this, where basically we have a bottleneck of these 3 edges here. If we were to try to draw the flow through this, we see that we can theoretically have a flow of 5 going out from S, and this would be able to handle that capacity as well. But eventually we get bottlenecked by these 3 edges. All of our flow has to go through these 3 edges, and so we cannot achieve a flow of more than 3 through from S to T. What we're going to do is we're essentially going to find one such flow path that can handle a capacity of 1, and then find another, and then find another. And we should have exactly up to 3. What we're going to do is we're going to start from S, BFS to find a path to T, and then delete that path, and then do that again. We do that 3 times, and we delete all of the edges, and that should give us our separated components. After removing those paths, we should have cleanly cut these. And because of how the problem statement is defined, it should be impossible for there to be any other 3 edges that we can remove. And so we'll delete the whole path because any of the other edges along the path will not matter. If we delete any 3 edges in this component here, when we delete the whole path, it won't disconnect the graph because we're guaranteed that these 3 edges are unique. So for this one, we'll need the graph again. And we'll also need deck. So So that gives us our graph, and now we just BFS a bunch of times and delete the path each time we go. So we'll pick a random start and end point. So we'll need to do this potentially many times. So, okay, technically this is a random algorithm because we pick a random start and end value, but it's guaranteed to eventually work. So we can say we can say nodes equals list of graph, and then we can say for I start in enumerate nodes, for end in nodes up to I, we can do some computation here. So let's extract that to a function. Def calc. We'll need to produce a copy of graph. So we can say graph equals dict of graph. And so that will give us a copy. Let's see what this gives us. Oh. Right. So that gives us a copy of the graph. And now we will make this return the answer if it finds it and none otherwise. So answer equals calc. If answer is not none, then we'll print it and exit the program. So basically we try every possible pair and eventually one of them will return the correct answer. The probability should be close to half. Basically we need to pick a start and end that are in opposite components, but of course we don't know what the components are yet. So this will have a 50-50 chance of working each time, so as we run it more and more times, it will become more and more likely. And because we're not doing it randomly and we're going through all the nodes in order, every time we fail, the probability of failure becomes slightly lower because we're running out of pairs that are in the same component. And so eventually we're guaranteed for this to work, but it might take a long time if we get really unlucky, which is very improbable. Okay, so we will BFS through the copy and delete the path each time. So for blank in range 3, we will apply this operation 3 times. So Q equals... Oh, sorry, I forgot to feed in the start and end values here. For each time, we will start with a Q that contains the start value, a scene set that contains the start value, and a parent dictionary again for the path backtracking. Now we can do while Q, node equals Q.pop left. For NX in graph node, if NX not in scene.add NX, Q.append NX, parent of NX equals node. And we could also exit as soon as we see end. So if NX equals end, we can break, break, else continue break. This thing just pushes up the break. So if we break here, then it'll skip the else and break out of this as well. If this doesn't break, then the else will run and it'll continue back here and skip this break. I apologize for this being a bit confusing, but Python doesn't have a way to break out of outer loops. We can set a flag, but I hate that. I guess you could also do q.clear and then break. Yeah, I guess this is a bit cleaner. We clear out the queue and then break. So then after it breaks out of this for loop, we end up here. And then queue is now empty because we just cleared it out. I'm going to go grab some water before continuing this real quick. My throat is getting a bit dry, so I'll be right back. All right. So after we've done this, now we want to backtrack from end to start and delete all of the edges. So we'll do the same thing as earlier. Node equals end, while node is not start. NX equals parent of node. And then eventually we'll do node equals NX. And in the middle here we can do graph node dot remove, copy node dot remove NX and copy NX dot remove node. And so after we do this 3 times, copy should now be short 3 edges. And so now if we do a not short 3 edges, short 3 paths. So now if we do a breadth first fill, if we have successfully disconnected the components, we now have 2 components that are split by those 3 edges. But if not, we have 1 component, and so we'll do a breadth first fill again. So Q equals dec from start. It doesn't matter which node we pick here. Oh yeah, and this should be copy, not graph. For NX in copy node, if NX not in scene.add NX, q.append NX, and if NX is equal to end. So if we manage to BFS from the start to the end, that means that we haven't successfully disconnected the components, and so we can just return none. If we complete our breadth first fill and we haven't reached the end, that means that we have now successfully disconnected our graph. And so now we can do A equals length of scene, B equals length of copy minus length of copy, length of graph will be the same thing, minus A, and then return A times B. Q error JQT, not in parent. Oh yeah, wait. Why is that the case? That's a bit confusing. Considering every node we reach should need to be through this, right? And how is it possible that we do not find the parent of a node? Okay, so it's failing when we start from XHK and go to JQT. And the current node is JQT, so the end node. So the end node does not have a parent? How is that possible? Because in theory, it should be impossible for us to disconnect the graph in only 2 paths, I believe, right? Because if it's possible to disconnect the graph by using 2 paths, that means that those 2 edges in those paths could have been removed to disconnect the graph. And so that's not possible, I think. I guess we can say here that if end is not in scene, okay, so at some point during our BFS, we're getting that we're not reaching the end node, but that doesn't feel like it should be possible. So what's going on here? For NX and copy node. NX not in scene. Oh, I get it. Because we're not actually cloning the graph properly. Because this creates a copy of graph, but the lists within the graph are not copied. So we need to manually copy this. Okay, I see. Yeah, so that's the thing about Python dictionaries. It's the same in most languages, really. But when we create a copy of graph using dict, it creates a shallow copy. And so anything inside of graph is not cloned, and we have references to the same thing. I also use networkx and minimum edge cut as well. But I wanted to show a solution that doesn't just rely on a library. So, okay, this will successfully create a copy, and this should now work. So, okay, now we have an answer. And this actually runs fast. It actually runs faster than networkx's does, I believe. Let me pull up that solution and see if this is faster. Yeah, this solution actually works faster than the networkx solution because the networkx solution has to... I don't know how minimum edge cut is done, but it's probably slower than this because for this one, we can rely on knowing that there are exactly 3 edges that we need to remove. So to recap this solution, this is my favorite solution. I don't know why I showed the other 2 first. I guess saving the best for last. This one, the reason I like it more is because it's way faster. It's much simpler as well by comparison. And although this technically does have a theoretically worst case pretty bad runtime, it's very unlikely that we'll need to run this more than a handful of times to eventually find the correct answer. So to recap, we observe that it's actually a property of networks, and I won't prove this is true, but the minimum edge cut, the minimum cut, that being the minimum number of edges that we need to sever to disconnect start and end, is equal to the maximum flow, which in this case is 3. Minimum edge cut finds 3 cuts. Yeah, I am using minimum edge cut in the solution I showed in my video. We just take the minimum edge cut, remove those edges, and then find the connected components. But I like this solution a lot more because we actually implemented the logic ourselves. And so basically, to find those 3 edges, we just BFS a path from the start to end, delete the whole path, and then just rinse and repeat. And after we do that 3 times, we should have disconnected the components. If not, that means that our start and end points were on the same half of the grid of the graph. And so it's possible that we disconnect these 3 paths, but then there's like a 4th path. In fact, there's always a 4th path if we're on the same component. Otherwise, disconnecting 3 edges would have cut the graph at a different position, which is impossible. And so after we run this 3 times, where each time we do a breadth first search, find the end node, and then disconnect all of the path in between, we do another breadth first fill. If we ever reach the endpoint, it means that we didn't successfully sever the graph in 2 components. And if we don't, then we can just take the size of the component, derive the size of the other component, and return the answer. Oh, you accidentally did it in DFS? That's rough. Wait, why would DFS not work though? Because you just need to find a path. It doesn't need to be the shortest path. Oh, wait, no. It does need to be the shortest path because otherwise you might... Yeah, I see. Because if it's not the shortest path, then you might have a situation where you go back and forth along the path and cut multiple of the edges at the same time. I guess that would be a potential problem. even then, it feels like that shouldn't be too difficult to get around. No, but you might end up cutting too many edges on one side of the component and then splitting off. Yeah, you might end up cutting too many edges on the left side. So yeah, I guess it is important that you find the shortest path. In any case, I think that's all we really have to go over for this stream. So I'll stick around for some more time if anyone has any more questions or any other interesting ideas or solutions they want to propose. But otherwise, I hope you guys all had a good Christmas, and I hope you enjoy the rest of your holidays as well. I looked into Karger, but isn't that a random algorithm? Like, I think it's also like a random chance of working. I guess all of the solutions that I've used so far are also random, so wouldn't hurt to use that. But yeah, I did take a look at Karger's solution. The app I use for drawing is Excalidraw. Yeah, Karger seems interesting. Collapse 2. Yeah, it's similar to the path contraction thing from the slopes problem, but not exactly. What is it? You just take two nodes that are adjacent, and then you just collapse them into one node and join all of their edges together. Like, sorry. So like, if you have a node here and a node here, and this one's connected like this, then you just merge them into one node and connect all of their edges like that. And then you keep going until you only have two nodes left. And if those two nodes have three edges between them. Okay, I see. Okay. And so if we imagine a theoretical graph with three... Actually, let's use the test data. Okay, so let's suppose we have this graph. I don't think these graphs can be nicely formatted, but what were the three edges again? NVD JQT, so that one. CMG BVB, so this one. And HFX PZL. Okay, so we have so let's fix these, the three that we need to use to split them apart. Okay, so these are the three edges we'll need to eventually disconnect. And so what do you do here? You just pick two random nodes and contract them, and join them, and then eventually you'll have just three edges between the two remaining nodes. And so I'm assuming if the nodes you end up with are on opposite sides, then this works, right? So like, let's suppose we randomly strike out this node. And so we end up joining these edges. So if we remove that, then these are already connected. I guess we'd also connect these two together if we struck at this node. They could have many remaining edges between them. And does this only give a valid answer if the number of remaining edges is 3? Is that how it works? Because I looked into this solution, but I didn't quite understand it. There's only one solution where they have 3 edges. Okay. So this is already connected. So we basically just keep randomly striking out nodes. And then eventually we'll end up with one node on this side and one node on this side. And the 3 edges between them will be these 3. Is that the idea? And if there are more than 3 edges, then we just try again with a different random contraction. Okay, I see. That's very interesting. Yeah, I'll definitely look into that solution in my own time afterwards then. That's a cool idea. Yeah, I saw Karger's algorithm as one of the solutions, but I didn't understand how exactly it would work here. Okay. Yeah, I mean, I would just create a copy of the graph like I did with my previous BFS solution. Yes, you only... Okay, that's interesting. I'll definitely take a look at that, thank you. Yeah, sure. If you want to send it on my Discord, that's probably the easiest way to share it. You can also just put a link in the stream chat if you'd like me to take a look now. Although I can give you some more thorough commentary if you put in my Discord later, because I don't have too much time right now. I have some plans with my family in a bit, so I will be leaving in like about 10 minutes or so. Thank you. Happy holidays to you as well. I'm glad you like the drawing parts. Yeah, I think visual explanations and demonstrations of the concepts are definitely helpful for the learning process. Just going through the code directly is not always the most important part of the learning, I think. So I'm glad you enjoy it. The Discord, let me get the link. I think it should be on my channel page, but I'll copy the link over. Give me a second. There we go. Okay, let's see. Oh, you're using Ruby. I am not familiar with Ruby, but this looks readable enough. Okay, so you have a node with a node count. So I'm assuming that's the number of nodes that you've collapsed so far. Oh, I see. And after you do your contraction, you don't even need to remove the edges because you now have two nodes that contain the size of the component that you collapsed into it. That's clever. And neighbors, of course. Okay, initially the node count is 1. So you go through input to build your graph from data, which is as a function argument. For each you... Okay, so this makes sense. You're just building up the neighbors. And hash is your hash map. And you're adding... Okay, I see. To collapse wall graphs is 2. You take... I'm assuming dot sample is random. You take a random node and a random neighbor. You delete the edge between them. You add all of these neighbors into U. Makes sense? And then you increase the node count, so you you join the two together. And then for each of V's neighbors, you remove V from it and reassign that edge to U. And then you delete V from the graph. Okay, I see. So while true, you build up a graph from the input, set the size, collapse the graph, and then partition is the size of collapse graph dot first dot last. Not sure I understand that part, but okay. And next, I'm assuming is similar to continue. So unless the size of the partition's neighbors is 3. So, okay, so partition is one of the two nodes. So unless that is 3, you skip. And once it is 3, you print out the partition's node count times the other partition's node count. Nice. Yeah, I can't think of too many better ways to do this. I guess one way I do this is instead of using build graph each time, I would just store the original graph, and then each time I collapse it, I would just create a copy, I guess. That's probably what I would do. But okay, I really like this solution. This is very clever. So yeah, my only feedback on this, I don't think I really have all that much to say about it. I wonder if you could optimize this by storing your graph as an edge instead of as an edge list instead of an adjacency list. So that way each time here you just select a random edge instead of a random pair of nodes because it's the same thing. And then, no, but then remapping all of the edges to the new node would be the same time complexity. Yeah, no, I like this. I think this is a good solution. And implementation wise, I can't think of much to comment on. Although I don't know Ruby at all, so I can't really comment on the implementation details too much. But yeah, I think this looks like a really neat solution. It's definitely a lot simpler than I thought it would be when I first read about the algorithm when I was researching. So yeah, neat solution. Thanks for sharing. Yeah, I'm always happy to learn. And I mean, like, a lot of the solutions I've presented, honestly, I didn't even come up with myself. Like, a lot of the solutions I've presented have been ones that I've learned from other people. So, yeah, although I do have a lot of experience, I am always learning. And I think it's impossible to know everything. And so being willing to always learn more is, I think, more important than the actual amount of knowledge anyone has. So yeah, thank you for sharing. Oh yeah, somebody asked what switches are in my keyboard. The keyboard that I'm using is this one, and the switches I'm using are the which ones? I think they're the green ones. Yeah, the green ones are the no, the green ones are the clicky ones. I'm using the yellow ones. Yeah, the yellow ones are the linear ones. So yeah, I'm using the Razer Black Widow V4 with the yellow switches. Um, yeah, and full disclosure, I'm not sponsored by Razer. This just happens to be the keyboard I picked when I was switching my keyboard recently. I was using a membrane keyboard up until this point. Okay, in any case, if there are no other questions, then thank you all for tuning in, and I will continue uploading content related to competitive programming and general coding topics after December. Though I will probably take a break from it for a bit since, I mean, I just went through a month of making daily videos, so I will probably take a bit of my Codeforces username. I don't remember. But yeah, it is just, I'll put it in the chat, but I mean, it's the same as the name I use everywhere. So yeah, if you are interested, that is my CF username. Anyway, yeah, thank you all for watching. If you have any other questions, just leave them in my Discord and I will answer them. But otherwise, happy holidays, everyone.